Section 1.6 is transformations and graphs. So what we're going to talk about in this section is let's take a function and we want to shift and move it around. And so we've listed out here, right, all the possible moves. C in this case stands for a real number that we could do, a constant, right? And then over here, we actually explain what those shifts and translations do. So one thing that I want to make sure you keep in mind with this is changes to the outside of the graph have a little bit different meaning than when we change things on the inside of the graph. So changes on the outside are pretty direct. And you can see that in the first line here. So if I add, right, 2 to every value of f of x, right? And remember, f of x are just the y values that came out of the original function. Well, if I add 2 to every one of those numbers, I'm increasing all the y values by 2. So it would shift the graph vertically upward. So that's what we have a plus over a minus. I'm saying upward goes with plus, right? Conversely, if I subtracted 2 from every one of my y values, well, I'm making all the y values 2 units smaller, and so the graph would shift down by 2 units. However, if we make that same change on the inside of the function, right, so you can see it's inside these parentheses of f of x, well, now if I add 2 values, or 2 units to all the x values before I evaluate the y, it actually shifts the unit, or the graph, 2 units to the left, right? Here, if we subtract 2, it's going to shift to the right. So here, plus and minus went with up and down, which made sense, right? Positive y is up, negative y is down. But here, notice it's the opposite movement of what you would notice. So when we actually do our next example, I'm going to show you that the reason the changes on the inside of the function appear to have the opposite effect of what you did is actually due to algebra. So when we actually do the algebra steps to unpack those moves, you'll see why it looks like it has that reverse effect, right? Negative on the outside, right? Negative 1 on the outside is taking every positive y value and making it negative. It's taking every negative y value and making it positive. So it makes sense that visually it reflects it over the x-axis. On the inside, you're negating all the x values before you evaluate the function, and that has the effect of reflecting it over the y-axis. Similar here when we multiply, right? If you multiply on the outside by c, it's going to stretch or compress the graph vertically by a factor of c. So if c is a number bigger than 1, it's going to make the graph taller. If c is a number between 0 and 1, it's going to make the graph shorter, right? So if c is 1/2, it's going to cut all the y values in half, right? It's going to shrink, compress it down. But when we do that on the inside, we're doing a horizontal stretch of compression, but it's actually going to have the opposite effect. So multiplying x by 1/2 would actually stretch it by a factor of 2, but multiplying x by 2 would actually compress it by a factor of 2. And the reason it's the opposite of what it seems like is once again due to algebra. So know when we ask you to do multiple movements, if we ask you to do the movements in a specific order, like on a list, then you do them in that order. But if we just say make all of these moves, or you see an equation where several moves have been made, there is sort of an order of operations to make sure the graph ends up in the desired place we wanted. So the order of operations is do all the reflections first, then do all the stretches, then do all the shifts. The only exception to this is if we specifically say do them in a different order. We want you to do one thing, then another, then another. So let me show you an example of what we mean, right? So we have the graph of g of x equals 2 times f of x plus 1 minus 1. And they want you to draw this new graph, right? Given the graph of the original f of x, you have to list all the transformations you made and make sure the points end up in the specific correct place. So the first thing that I like to do when I'm doing a problem like this is I like to label any identifying points that are kind of like markers for me. So I know this graph has a weird zigzag, and I want to make sure that these 4 points have hit the correct corresponding place on the next graph. So I'm going to label their coordinate points. So this one is -2, 0. This is point -1, 1. This is point 1, -1. And this is point 3, 1. So if I look at my equation here, what's happening is there's a 2 on the outside, So the first thing that's I see happening here is this graph is stretched vertically by a factor of 2. The +1 on the inside is shifting 1 unit to the left, right? So it feels like you should be going right, but it's on the inside of the function, so we really go left. Then the -1 on the outside is shifting you 1 unit down. So we could try to sort of intuitively make these moves on these points, but there actually is a way to algebraically do it to make sure we end up at exactly where we need to go. So what we want to do is we want to look at the moves on the inside separately from the moves happening on the outside of the function. So this is, right, outside. This is on the inside of the function. And this is also on the outside of the function. So for moves on the inside of the function, set the expression inside equal to the original x value and then solve for the new x. All right, so let's see what I mean here. So if we look at our equation, there's the expression on the inside of this function. So if I take x, this is the old original x values, right, +1, there's my expression, and, oops, sorry, this should be new x, right, set it equal to the old x value, and now solve for x, I'm going to get that the new x's should just be the old x's minus 1. So now the shift left should make sense, right? Because we're going to take all of the original x values and subtract 1 from them, and that will move the graph to the left 1 unit. For the outside of the function, plug the old y values in for f of whatever's in here. We ignore it. We just, wherever we see this in the function, right? And the new y comes out, okay? So for our expression, it's 2 times, right? We had f of x plus 1, so that's old y, right? Minus 1 equals new y. So we can actually do this very quickly on all of our points. So I'm going to list out the identifying points and we're going to map them to their new location. So the 4 points we want to do this for are -2, 0, -1, 1, 1, -1, and 3, 1. And what we're going to do is we're going to figure out where those points moved after all those moves were made. So let's do the x values first. So we actually have an equation for that. This just says we'll take every original value of x and subtract 1 from it. So -2 minus 1 is -3. -1 minus 1 is -2. 1 minus 1 is 0. And 3 minus 1 is 2. Now I'm going to take all my y values and I'm just going to plug it into the equation directly. So it was 2 times f of stuff, those were the old y values, and then subtract 1. So you just follow the normal algebra order of operations, and that takes care of all the moves in the right order. So 0 is our first value. 2 times 0 is 0. Minus 1 gives me -1. 1 is our next value, so 2 times 1 is 2. 2 minus 1 is 1. Now I have negative 1. 2 times negative 1 is negative 2. Negative 2 minus 1 is negative 3. 1 times 2 is 2. 2 minus 1 is 1. So now if I plot these new points and connect my dots, I should end up with my graph. So negative 3, 1, excuse me, negative 3, negative 1 is here. Negative 2, positive 1, 0, negative 3, and 2, 1. And when I connect my dots, I can actually compare these two graphs now, and I can see that every x value shifted over 1 point from the original graph. The graph got stretched by a factor of 2. So this was only 1 unit height and difference, now it's 2 in difference, right? These were 2 y units apart, now they're 4. These were 2 y units apart, and now they're 4. And so this is now the graph of g, where g equals 2f of x plus 1 minus 1. So this takes a little bit of practice, but now hopefully you can see it's when we actually do the algebra, right, all those moves end up becoming the opposite of what we expected.